From the Global Newsroom in Toronto, NewsHour.
Hi, I'm Jocelyn Thomas.
And I'm Jacob Stewart, and this is the news at 11.
On today's agenda, we're going to talk about hydrocracking.
This is the process of breaking large hydrocarbon chains into smaller, more usable hydrocarbons. The long chain of hydrocarbons is combined with hydrogen steam and placed under extreme heat and pressure, which cracks the chain and produces smaller hydrogen chains. Catalysts, such as alumina, silica, or zeolates, are present throughout the process as well. This process converts petroleum crude oils with a high boiling point into lower boiling point hydrocarbons such as kerosene, gasoline, jet fuel, and diesel oil. Carbon-carbon bonds are broken and the excess hydrogen present attaches to the carbon ends. Any sulfur or nitrogen that is present in the fuel will react with the hydrogen to form hydrogen sulfide and ammonia. This is an image of the hydrocracking process. An example of this would be heptane, a large chain of hydrocarbons splitting into propane and butane. These two molecules have much lower burning properties, which make them more efficient gases. The diagram below shows that hydrogen atoms are added to the chains to replace the empty bond in the carbon atoms that have recently split. Now back to you, Jocelyn.
Now we're going to talk about catalytic reforming. Reforming takes straight-chain hydrocarbons in the C6 to C8 range from gasoline or other naphthas and rearranges them into compounds containing benzene rings. Hydrogen is produced as a byproduct of the reaction. Similar to hydrocracking, a catalyst is present with the hydrocarbons and the gas is heated to a very high temperature and pressure. As an example, hexene, which is C6H14, loses a hydrogen and turns into benzene, an aromatic. Aromatics have better burning properties than long chains do.
From the Global Newsroom in Toronto.
Hi everyone, and I'm a representative from oilandgas.ca, and I'm here to explain to you the differences in octane ratings, which is exactly what we deal with here at oilandgas.ca. Octane rating is a measurement of a type of fuel. Fuels with higher octane ratings perform better, meaning that the gas can withstand more compression before combusting. These higher octane fuels are used in high-performance engines. Increasing the octane rating of gasoline can result in better performance and mileage on existing vehicles. Better mileage means less money spent for you and less environmental impact, which is exactly what society needs. This is why companies like oilandgas.ca are working to create gasolines with higher octane ratings. A lower octane rating means that the gas cannot take as much compression before igniting. A low octane rating is ideal for diesel engines because rather than compressing the fuel, they compress the air and then inject the fuel into the heated and compressed air. Low octane ratings are often paired with high cetane ratings, which is a measurement of the speed of combustion of diesel fuels. Cetane numbers can help to determine the quality of a diesel fuel. Diesel fuels with high cetane numbers will have similar amounts of time between the first injection of fuel and the first noticeable pressure change as the fuel combusts. A higher cetane level means that the delay will be less, so there will be a more complete combustion, which means smoother running of the engine and less harmful emissions. So if you have a diesel engine, that's perfect for you. Society needs better quality fuel to pair with the high quality engine production from car companies these days. So oil and gas companies like oilandgas.ca must produce fuels with higher octane and cetane levels. So, now that you know a little bit more about octane and cetane levels, you should check out oilandgas.ca and learn more about what we produce for you. Call or click today. Thank you.
From the Global Newsroom in Toronto.
Back to you, Jacob.
We're going to talk about bitumen. Bitumen is extra heavy oil. The first step in the upgrading process is to remove the naturally occurring light gas oil component of bitumen and to recover the naphtha. This is done in the 3 diluent recovery units, which operate much like an atmospheric distillation unit in a conventional refinery. The light gas oil stream is sent to the hydrotreaters. The diluent naphtha is recycled to the extraction plant, and the bottom's atmospheric top bitumen is predominantly fed to the vacuum distillation unit, or VDU, with a modest amount going directly to the conversion units. The VDU removes all of the remaining light and heavy gas oils, directing these streams to the hydrotreaters. The bottoms from the VDU vacuum top bitumen are fed to the conversion units. Fluid cokers are used to crack large bitumen chains into shorter, more usable molecules. These shorter chains are heavy gas oils, light gas oils, and naphtha. The fluid coking process is a continuous operation where fluidized coke particles are constantly transferred back and forth between the reactor and burner vessels. The bitumen is then transferred to a hydrocracker where it is put through an ebullited bed process that uses catalyst and hydrogen to convert bitumen into gas oils and naphtha.
That really is bitumen, Jacob.
Oh, you bet it is bitchin'. Now back to you, Joss.
Now we're going to talk about methanol. Methanol can be made in a variety of ways, and thus it is a very flexible commodity in the oil industry. Synthesis gas must first be created, which can be produced from anything that was ever a plant, and is mainly composed of carbon monoxide and hydrogen gas. There are two steps to creating methanol. The first is to convert the feedstock into synthesis gas, which is typically done through catalytic reforming, as was explained before. The second step is to form methanol out of the synthesis gas. The reaction for this is shown below. Back to you, Jacob.
Now we're going to talk about ethylene glycol. Ethylene glycol can be produced from ethylene by first oxidizing the ethylene to become ethylene oxide, which can then be reacted with water to form ethylene glycol. Shell, the multinational oil and gas company, uses a process known as the omega process, which uses this ethylene oxide and CO2 to produce ethylene carbonate, which is then combined with water to produce which is then produced with which uses this ethylene oxide and CO2 to produce ethylene carbonate, which is then combined with water to produce ethylene glycol. When the ethylene carbonate is hydrolyzed, the CO2 is released and fed back to the original circuit. The reactions for this process are shown below. Now back to you, Jocelyn.
Now we're going to talk about polyethylene. Ethylene, the monomer of the polyethylene chain, is a rather stable molecule that can polymerize upon contact with metal-based catalysts such as titanium. The polymerization of ethylene to create polyethylene occurs in a high-pressure apparatus wherein radical polymerization happens. This is when a polymer is formed by adding several free radicals. The strong double bond between the two carbons in ethylene is destroyed so that each carbon can bond with two other carbons. The general formula for polyethylene is C2H4 multiplied by however many ethylenes there are. This is because C2H4 is the formula for ethylene, and N is the number of ethylenes stacked together. Polyethylene is the most common plastic and is often used across the world. This is what the structure would look like.
Really interesting stuff, Jocelyn.
Very interesting.
Now we're going to talk about polyvinyl chloride,
Wow.
or PVC for short. Don't test me. Polyvinyl chloride is a commonly used synthetic plastic polymer. Similarly to the production of polyethylene, PVC is created through the polymerization of the vinyl chloride monomer. Suspension polymerization is used to create PVC, which is a process that uses rapid agitation to mix the monomers into a liquid state where they can polymerize. And the diagrams are shown below.
Next, we're going to talk about urea formaldehyde. Urea formaldehyde is made from a combination of urea, which is a solid crystal found in ammonia, and formaldehyde, which is a very reactive gas obtained from methane. These two molecules are polymerized when they are placed under high heat and pressure and in the presence of catalysts such as alkaline ammonia molecule. These reactions result in condensation, which forms urea formaldehyde, and this is shown in the complex diagram below.
From the Global Newsroom in Toronto.
Hello everyone, this is a message from Valves and Stuff, warning you about the possible corrosion around your engine from none other than sulfur. A little message about sulfur. Fuels used in engines contain sulfur, which is transformed into sulfuric acid when it combines with water vapor during the combustion process. Sulfuric acid is then released to the environment and then returned to the earth in the form of acid rain. This acid is extremely corrosive, and responsible for degrading large areas of workable land. Not only is it dangerous for the earth, but it can also be harmful to engines, as it can wear out the valve guides and other engine components. As a result of this, oil companies have worked to remove sulfur from engine fuels. Most countries that produce oil have regulations in place to control sulfur content now. Low sulfur and ultra-low sulfur diesel fuel is now used in non-road, locomotive, and marine engines. The EPA stated that these new low-sulfur fuels will reduce emissions by 90%. But this has not been installed yet, so you should check the valves around your engine, and if there's any corrosion, you should call us at 1-800-CHECK-NOW. A quick message from Valves and Stuff. The Klaus process, which is shown in the diagram here, recovers sulfur from gaseous hydrogen sulfide found in natural gas. The chemical formula for this is shown below. The Klaus process is a crucial part of our business here at Valves and Stuff. It is exactly how we extract sulfur from natural gas.
Nanotechnology, the newest and greatest investment. A propin is typically a sand, treated sand, or a man-made ceramic material. It is designed to keep an induced hydraulic fracture open during or following fracture treatments. Propins are pumped into ultra-tight rock formations during hydraulic fracturing treatments to create pathways for oil and gas to flow into the wellbore. Given the steep decline on most shale and tight sand wells, the industry is searching for lighter yet stronger replacements to be carried deeper into the formation without being crushed. This is where you, the investor, needs to give your cold hard cash to us. This is the point where nanotechnology is being introduced to the field. Propins can only travel about 100 to 130 feet with current technology, but a propin that can travel 180 feet or more and withstand the tight pressure in the formation is needed. This is where your investment will go and will make you big cash. Designing a better frac job could double recovery or double your money, and a more buoyant propin system would require much less pressure and fluid, both reducing cost and easing the need for large volumes of water, but not easing the need for your pockets to hold all that cash. A case in point is the ceramic propin technology originally developed in a laboratory. Unlike conventional sand propins, the manufacturing process of ceramics can be controlled at the molecular level to create perfectly spherical propins hundreds of microns in size that are hollow to add buoyancy. As a result of using this inherently simple molecular design, ceramic propins are very lightweight with a specific gravity and strength curve similar to more conventional propins. Ceramic propin research initiatives at Rice University have culminated on the commercialization of a product run by a new company spun off from Rice, Oxane Materials, which has started commercial propin production operations at a large manufacturing facility in Van Buren, Arizona. Nanotubes are made of carbon, sometimes only an atom thick. They have a tensile strength 20 times that of today's strongest carbon fibers, making them a strong candidate to become propins and making them a strong candidate to double the size of your wallet.
From the Global Newsroom in Toronto.
Hello and welcome back from the commercial break. Nanotechnology, that's interesting stuff, isn't it, Jacob?
Oh, you bet it is. I would spend my cold hard cash on that any day.
Now we're going to talk about burning fossil fuels and climate change. Burning any type of fossil fuel that contains carbon will release carbon dioxide, which will accumulate in the atmosphere. CO2 is a clear gas that will absorb the infrared radiation or heat from the sun and trap it in the atmosphere. This causes the Earth to heat up and thus resulting in climate change. Proof of this climate change lies in the sea level rise, global temperature rise, warming of the oceans, shrinking of ice sheets, glacial retreat, and decreased snow cover. Carbon dioxide is known as one of the greenhouse gases. The others include methane, nitrous oxide, and water vapor. 37% of man-made CO2 emissions come from the energy industry. The burning of coal has a greater impact on the environment than any other human activity. This is because coal is the most carbon-rich fossil fuel on the planet. While coal is a mixture of several different types of hydrocarbons, it is difficult to determine the formula. What we do know, however, is that the carbon atoms within the coal react with the oxygen to form carbon dioxide. Another type of hydrocarbon that is commonly burned is octane or gasoline. This, similar to coal, releases CO2, as is shown in the formula below. As you can see, for every mole of octane burned, 8 moles of CO2 is released into the atmosphere. Humans use octane in their vehicles, so a lot of this fuel is burned all over the world. Taking that into consideration, it is easy to see how troublesome it is to have that much CO2 accumulating in the atmosphere and heating it up.
Wow, truly devastating stuff.
Isn't it?
Now we're going to talk about the byproducts of common reactions. The primary pollutants of the combustion of fossil fuels include carbon monoxide, carbon dioxide, nitrogen dioxide, nitric oxide, sulfur dioxide, soot, and lead. Carbon monoxide is the most common pollutant produced from the combustion process, as the carbon in the hydrocarbon reacts with the oxygen to form it. Carbon monoxide and soot are common byproducts of incomplete combustion, which is when there is not enough oxygen to react with the hydrocarbon. Take methane, for example. It requires 2 moles of oxygen for every mole of methane burned to produce CO2. If there is any less than this, the CO2 won't be able to form properly. Sometimes there is additional carbon left over that doesn't pair with oxygen at all, and so soot is formed, which is just carbon solid. So the complete combustion and incomplete combustions are shown below. Sulfur dioxide is also a common pollutant, as sulfur is found in most organic compounds, including crude oils and coal. When the sulfur is not properly removed from the gasoline prior to its combustion, it will react with the oxygen in the air and produce SO2. This is dangerous as it is released in the atmosphere and returns in the form of acid rain, which can destroy land and man-made objects. Dioxins have been considered highly toxic and able to cause reproductive and developmental problems, damage the immune system, interfere with hormones, and also cause cancer. The suspected toxic effects in adults are liver damage and alterations in heme metabolism, serum lipid levels, thyroid functions, as well as diabetes and immunological effects. In line with animal studies, developmental effects may be much more important than effects in adults. These include disturbances of tooth development and of sexual development. An example of the variation in responses is clearly seen in a study following the Seveso, which was a chemical disaster in which a large amount of dioxin was released, disaster indicating that sperm count and motility were affected in different ways in exposed males, depending on whether they were exposed before, during, or after puberty.
Wow.
Dioxins are well-established carcinogens in animal studies, although the precise mechanistic role is not clear. Dioxins are not mutagenic or genotoxic. The U.S. Environmental Protection Agency has categorized dioxin and the mixture of substances associated with sources of dioxin toxicity as a likely human carcinogen. The International Agency for Research on Cancer has classified TCDD as a human carcinogen, class 1, on the basis of clear animal carcinogenicity and limited human data, but was not able to classify other dioxins. It is thought that the presence of dioxin can accelerate the formation of tumors and adversely affect the normal, inhibiting tumor growth without actually instigating the carcinogenic event. All groups of dioxin-like compounds are persistent in the environment. Neither soil microbes nor animals are able to break down effectively the PCDD/Fs with lateral chlorines. This causes very slow elimination. UV light is able to slowly break down these compounds. Lipophilicity, which is the tendency to seek for fat-like environments, and very poor water solubility make these compounds move from water environment to living organisms having lipid cell structures. Due to bioaccumulation and biomagnification, the species at the top of the trophic pyramid are most vulnerable to dioxin-like compounds. In Europe, the white-tailed eagle and some species of seals have approached extinction due to poisoning by persistent organic pollutants. Likewise, in America, the population of bald eagles declined because of POPs causing thinning of eggs and other reproductive problems. Usually, the failure has been attributed mostly to DDT, but dioxins are also a possible cause of reproductive effects. Both in America and Europe, many waterfowl have high concentrations of dioxins, but usually not high enough to disturb their reproductive success.
Wow, dioxins are just terrible for you.
Really
Wow.
scary stuff.
From the Global Newsroom in Toronto,
E10 Fuel. Buy it today. This blend contains 10% ethanol and 90% gasoline. This is why you should buy E10 fuel. Oxygenates are often added to fuels because they reduce carbon monoxide and soot production, which are common byproducts of incomplete combustion. Incomplete combustion occurs when there is not enough oxygen present to fully react with the hydrocarbon fuel to convert all of the carbon to carbon dioxide. This causes the additional carbon left over to turn into CO or C, which is carbon monoxide or solid carbon. An example of this incomplete combustion is shown. Methane will be used as an example to demonstrate complete combustion versus incomplete combustion. As you can see, the combustion of methane requires 2 moles of oxygen in order to create carbon dioxide. However, in incomplete combustion, there will be less than 2 moles of oxygen. For example, here there is 1.5 moles, and this means that there isn't enough oxygen to completely convert the carbon into CO2, and that's why CO is created. Ethanol contains 35% oxygen, so it is often blended with gasoline to add oxygen to the combustion reaction, which will minimize the amount of soot and carbon monoxide that's released from the gasoline as it burns. As ethanol is produced from plants, it is a renewable resource. Ethanol also displaces the use of toxic gasoline components such as benzene, which is a carcinogen. A common blend of ethanol is E10. And that, as I said before, contains 10% ethanol and 90% gasoline. More than 95% of the fuel sold in the United States right now contains up to 10% ethanol. So, if you want to make a difference for your environment, buy E10 today.
From the Global Newsroom in Toronto.
Now we're going to talk about recycling of plastics. Recycling plastics reduces the amount of energy and natural resources, such as water and petroleum, needed to create virgin plastic. According to the American Plastics Council, the production of plastic accounts for 4% of U.S. energy consumption, and 70% of the plastics in the United States are made from domestic natural gas. In the short term, recycling can be better than burning or burying plastics, and it can replace the use of virgin petroleum in making new products. However, even the plastics recycling process is not without harmful effects on human and environmental health. Plastic is melted during the recycling process, which causes it to break down and release the chemicals used to make it. Recycling plastics is associated with skin and respiratory problems resulting from exposure to and inhalation of toxic fumes, especially hydrocarbons and residues released during the recycling process. This is true of some types, like PVC, and many more. Heating and reheating plastic also degrades it, which is why plastic collected from recycling is often downcycled. Plastic bottles, for example, are made into carpet, fleece, plastic lumber, and other products that cannot be recycled again. This also does little to reduce the use of virgin petroleum to make new bottles. We cannot escape the toxins that are released from recycling, not even when they are released from overseas. Toxins do not stay local. Dioxins, for example, travel overseas in air currents, making them a global contaminant. Back to you, Jacob.
Really scary stuff, even though recycling is thought to be so good.
Yeah.
Turns out it's the worst thing in the world.
Well, anyways.
Just kidding. Recycle your bottles. Now we're going to talk about CFCs and HCFCs. A chlorofluorocarbon is not only a hard word to say, but it's an organic compound that contains only carbon, chlorine, and fluorine produced as a volatile derivative of methane, ethane, and propane. Many CFCs have been widely used as refrigerants, propellants, which occur in aerosol applications, and solvents. Because CFCs contribute to ozone depletion in the upper atmosphere, the manufacture of such compounds has been phased out under the Montreal Protocol, and they're being replaced with other products such as hydrofluorocarbons, which are HFCs, and hydrocarbons and CO2. However, these replacements are sometimes considered pollutants in their own right. CFCs and HCFCs are volatile in nature, and the CFCs have still higher boiling points because the chloride is even more polarizable than fluoride. Because of their polarity, the CFCs are useful solvents, and their boiling points make them suitable as refrigerants. The CFCs are far less flammable than methane, in part because they contain fewer C to H bonds, and in part because, in the case of the chlorides and the bromides, they release The released halides quench the free radicals that sustain flames. The reaction is shown for chlorodifluoromethane below. The most important reaction of the CFCs is the photoinduced scission of a C to Cl bond, shown below. The chlorine atom, written as Cl-, behaves very differently from the chlorine molecule, Cl2. The radical, Cl- is long-lived. I have to sneeze. The chlorine atom, written as Cl-, behaves very differently from the chlorine molecule, Cl2. The radical Cl- is long-lived in the upper atmosphere, where it catalyzes the conversion of ozone into O2. Ozone absorbs UVB radiation, so its depletion allows more of this high-energy radiation to reach the Earth's surface. Bromine atoms are even more efficient catalysts, hence brominated CFCs are also very regulated. CFCs are very stable in the troposphere. They move into the stratosphere and are broken down by strong UV light, where they release chlorine atoms that then deplete the ozone layer. The HCFCs are one class of chemicals being used to replace the CFCs. They contain chlorine and thus deplete stratospheric ozone, but to a much lesser extent than the CFCs.
Very interesting. Well, I hope you enjoyed the news at 11, and I hope you're a little bit more informed about industrial organic chemistry.
Thanks for tuning in.
From the Global Newsroom in Toronto, NewsHour.